Anyone have lab 2 questions? Is that going okay? I know this is a hard week. Anyone having any issues they want to talk about? I have one cautionary tale from when I was prepping some of the demos I'm going to go over today. Yesterday, I was trying to get one demo to run and it kept seg faulting. So I dug into that for like an hour and a half, and I couldn't figure it out. So I put the same Verilog and the same HPS code onto a different device, and it worked just fine. So then I swapped the SD cards in the devices, and it ended up being an issue with the SD card. So I put the image on the SD card again, and then it worked just fine again. But this is just to remind you that do not assume that those SD cards are safe places to store code permanently. I discovered this for myself yesterday. They might go bad. I don't know what exactly went bad in this one. It was a bizarre symptom, and maybe it wasn't even, you know, maybe it was something that, I don't know. I haven't figured out what the issue was, but something related to the SD card that reflashing it fixed. Okay. If there aren't any questions, I'll get into the content for today. Surprised so few people are here. I wonder if people are working on the lab checkout.
It might be that, but also I think some of the internet in Ithaca is down. That's why I had to run to campus, and I had an issue with getting on because I was using my phone.
Oh, that must be exactly it. It's like a Spectrum thing?
This was FiberSpark, but it might also be Spectrum.
Okay, good to know. Thank you. So what I'm going to talk about today is we've talked about at least one method for sharing information between the HPS and the FPGA through PIO ports, parallel IO ports. What I want to spend most of today talking about is a second method for sharing information between the FPGA and the ARM, which are through shared memory. So in QSys, you can put on-chip SRAM onto the Avalon bus and expose one slave of that. It essentially builds M10K blocks, but you can expose one slave of that on-chip SRAM into the Verilog and the other to the HPS so that you can have shared memory between the HPS and the FPGA, which can be really nice for some applications because it's persistent. So I thought I would walk through how to do that. Actually, very importantly, let me first show you. My parents got a new puppy today. This is a picture of him. His name is Cooper, and he's an 8-week-old lab. So very exciting news. Okay, so on-chip SRAM. I'm starting from the same essentially blank project that we started from last time. So this was the project that all that's going on in here is there's a counter that's overflowing and we're flashing an LED now and then. So if we open up the QSys, the only thing that's presently on this QSys bus is the system PLL and the ARM and nothing else. And we'll add some on-chip SRAM to this and then take a look at it. We'll take a look at how we drive it in Verilog and on the HPS. Oh, this is not as blank as I remember it leaving. That's okay. I'm just going to remove this stuff from here. This is artifacts from the last lecture that I thought I'd cleaned up, but apparently I haven't. So these were just the PLLs that we had added. Okay, so all that's presently on this QSys bus is the system PLL and the ARM. We want to add some shared memory between the FPGA and the ARM. So if we go in the IP catalog, basic functions, on-chip memory, and then on-chip memory RAM or ROM. There are a few other options in here, these FIFOs, for example, which there's some examples on the course website about setting up some FIFOs between the FPGA and the ARM, but today I want to talk about this shared memory. So when we open this up, there's a bunch of configurations. The most important one is we want for this to be writable, because we want to be able to write to it from the FPGA and read it from the ARM and vice versa. So not just a read-only memory block. I want dual port access, because I want to have two slave inputs to this memory, one that I'll attach to the ARM and the other that I'll attach to the Verilog. I don't care about read during write mode. Block type, I'm going to leave this on auto, but you can specify the type of memory that you would like to build here, either MLAB blocks or M10K blocks. I'll specify M10K. And then some relatively self-explanatory configurations. Data width, how wide you want for each address in your memory table, what's the width of the data that you want stored at that address? I'll keep that at 32. And then how big do you want for this memory block to be? That's configurable as well. I'll leave that at 4096. Kind of interestingly, if you make this big and the compiler realizes that you are not using all of that memory, it may optimize away some of the size of this memory block. So you can look at the compiler reports and see what the compiler is doing with your memory. But if you make this quite large and you only use a few addresses, which is what we're going to do today, incidentally, is only use a few addresses of this, the compiler may look at that and say, oh, he doesn't need that much memory. I can just give him as much as he's actually using. You can configure the read latency. Does it take 1 cycle or 2 cycles to read? Just for sake of throughput, I'm going to keep this at 1. You could, in principle, make it 2-cycle read latency. Oops. If you want, you can point this to a hex file to initialize it. I'm not going to do that. So I'm just going to leave it like this. We can finish this. We'll give it a name. Call it onchip SRAM. And then we can make a number of connections. I am going to add one more thing to this bus, which is a clock bridge. So clock bridge. And I'll give this a, oh, just let me edit this. I'm going to give this an explicit clock rate of 50 megahertz, I think. I wrote this down. Yeah, 50 megahertz. And I want to make that 100 megahertz, but for some reason it's not allowing me right now. I'll figure out why that's the case. In any case, I want to hook up the system clock to the input of this clock bridge and hook up the on-chip SRAM clock 1 input to the out clock. This is giving me a 50 megahertz clock to run this on-chip SRAM, which is the same speed that we're going to be running the state machine in Verilog, so that it matches. Slave 1 here. So as I mentioned, we have 2 slave inputs here, 2 reset lines. I want one of these slave inputs to be exported into the Verilog, and then I'm going to expose the other one. I'm going to connect the other one to the AXI bus in the ARM. So slave 1 here, I'm just going to export into the Verilog like so. I'm going to hook up the resets to the system and the ARM reset lines. Slave 2, I'll hook up to the AXI bus. I'll hook up clock 2 to the system clock. And then I'll hook up reset 2 also to the 2 reset lines. And then we can come over here and look at the memory offset here. We currently have this just at an offset of 0. and that's not overlapping with anything presently, so we'll just leave it there for the time being. So we can save this and generate it. And then I want to show you the signals that then appear in your computer system.v file. Is this laggy for you? My internet appears to be a little bit shaky. I'm getting some okay connection sort of hand signals.
Working okay out in the wilds of Hector.
Okay. This remote desktop connection was a little unstable this morning. I'm not sure why that was, but hopefully it holds together. Okay, so let's take a look at so that is generated. And then if we open up our computer system.v file, we can see what's appeared from that exported slave signal. Down here, it is all of the signals shown here. So these are the signals that we can now hook up to our own Verilog in order to control that slave input, to write information to this memory block. So I will, I could copy this here, and as usual, place it down here and hook it up to our own Verilog. Because we've done this a number of times, I'm gonna skip that and jump to a project where I've already hooked these things up so that you don't have to watch me do that for the 4th or 5th time. So I'm going to close this project. And take a look at this one, where I'll open up I'll have that open up, but this is exactly the same project that we were just looking at, just hooked up. So down here, all of those signals that we just looked at in the computer system.v file, I've connected them to our own signals in the Verilog. And then I'm going to show you the state machine that's running to manipulate these different lines. So the signals that we get are, we have an address line where we'll specify the address to which we want to write or from which we want to read. We have a clock enable line, a chip select line that will end up just holding what, low or high. We just want this always enabled. We'll hold it high. A write enable line, a line from which we read the data back from memory, a write data line, and then just like on the busmaster, we have a byte enable where we specify the number of bytes that we want to write. And in this case, we have this at 4 bytes because we're writing 32 bits to each memory address. So this is just exactly the same QSys that we just set up. But we can take a look at the state machine that's up here. These are the declarations for all of the wires that we hooked up the QSys generated wires to in our own Verilog. So we have a 32-bit wide read data line, because when we read from an address, we specified in QSys that the data was going to be 32 bits wide, so we have 32 bits to read here. We'll store the data that we read in a 32-bit register called data buffer, and we'll store the data that we're going to write into a register that we're calling SRAM write data. Our address is a 10-bit wide register, 10 bits because in QSys we said that we wanted 4,096 rows in our M10K block. So we need 10 bits in order to write to each of those addresses. A write enable line. There is no read enable line. It will do reads. It will automatically be reading from the address that you specify in the SRAM address register. But if you want to write, then you assert the SRAM write bit. A clock enable, which we're holding high because we just always want this active, and a chip select, which we're also holding high. And then a register that we're just using to drive our state machine, our state variable. And then what we're going to actually have this do, we need some, because we are sharing memory between the FPGA and the ARM, we do need some sort of handshaking between the FPGA and the ARM so that they aren't competing with each other to read and write from the same memory addresses at the same time. So that handshaking is going to take place. We're going to use the address 0 of our on-chip SRAM as the mechanism for doing these handshakes. So when the HPS puts any data into address 0, the FPGA will read that and say, okay, now it's my turn to manipulate this memory. And then it will deassert that. And when the HPS sees that the FPGA has has set the data contained in address 0 back to 0, that will be the signal to the HPS that it can manipulate the memory. So the first thing that we do here in state 0 is we set the address from which we want to read to 0. We deassert the write enable because we don't want to write any memory, we just want to read. And then we drop into state 1. You'll recall that this is building M10K blocks. So all of the same rules for reading and writing to M10K blocks apply here. And one of those you'll recall was it takes 2 cycles to read from an M10K block. So we need to delay for 1 cycle before our data is available to be read here. So we set our address, we deassert write enable, we drop into state 1, delay for a cycle and drop straight into state 2. We store the information that's on the SRAM read data line in this data buffer. Keep the SRAM write signal deasserted because we're still not doing a write, and then we drop into state 3. In the case that there is a value greater than 0 contained within memory address 0, that is the signal to the FPGA that it's its turn to do memory manipulation. So in the case that there is information in address 0, so in the case that data buffer is greater than 0, then we assert the write enable because we want to do a write. We set the address that we want to write to 1, and then the value that we actually write to address 1 is the value that was contained in that data buffer plus 1. This is just so that we're writing something predictable so that we can tell, it is easy to tell whether this is working or not. So on the HPS side, we'll put a value into address 0. The FPGA will read that value out, increment it by 1, and store that value in address 1. And then it'll drop into state 4. And by the way, if there wasn't any data in address 0, then it just goes back to state 0 to keep waiting for the HPS to put some information in address 0. But okay, so this has, we've done a write enable, we've specified the address, we've specified the data that we want to write, and then we drop into state 4. Recall that it'll do a write in 1 cycle. So by the time we get to state 4, it has written to address 1. We then want to signal back to the HPS, this is the handshake, we want to signal back to the HPS that on the Verilog side, we're done manipulating this memory. So we're going to do that by doing another memory write. So we're going to assert the write enable. This time we're going to write to address 0. That's the handshake address. And we're going to write a 0. And this will be the signal to the HPS that we're done doing stuff with this memory. It's your turn again. And then we go back to state 0. that make sense? So in this case, we're only manipulating addresses 0 and 1 for this sort of canned little toy demo. You could, in principle, write the on-chip SRAM that we built for this example had 4,096 rows. So you could write to addresses 0, 1, 2, all the way up to 4,096. And you could make it even bigger than that. So you can get a lot of persistent shared memory between the ARM and the FPGA, which could be very useful. Might be useful, for example, if you're trying to get the information about the state of your drum out to the FPGA so that you can ultimately get it out to MATLAB to do something like a power spectrum for it. You could do something like this. Now, this comes at a cost in that case. If you have filled your FPGA with as many M10K blocks holding drum information as you possibly can, recall that the way that we've set this up, we're using some M10K blocks. So we would have to sacrifice some of our drum M10K blocks in order to build this shared memory between the ARM and the FPGA. But you could do that. Okay. I'll program the FPGA with this. I think it's already programmed with this, but I'll just make sure. And then I want to look at the HPS code that's associated with this. So if we go look at the HPS, this is the code that's running on the HPS. We do a lot of the same, this looks structurally extremely similar to when we were building, when we were writing HPS code for PIO ports. It's the same sort of memory mapping. We're just mapping to different locations in memory. But very similarly to before, we declare a pointer to an unsigned int. And then we open up, we do this thing where we open up memory as a file, right? And then we do an mmap to the location in memory where this shared memory between the HPS and the FPGA lives. Now, when we were doing, when we were mapping PIO ports, the PIO ports, if you put them on the AXI bus, they were put on offsets from the from address C0. In the address ARM BRL4 file, it is given the name SDRAM base, but the PIO ports on the AXI bus were placed at offsets from this base address. The base address for the on-chip SRAM is different. So far as I can tell, I dug into this for a while yesterday, and so far as I can tell, the on-chip SRAM's base address is at this FPGA on-chip base at address C80000, etc. So when we're mapping this SRAM, or when we're mapping the location of this shared memory, we are doing so with this on-chip base as the base address, as opposed to C0, it's C8, etc. Does that agree with your understanding, Bruce? This is what I was able to gather from digging through this, but I want to make sure I'm not getting this wrong.
I'm not sure that's right. Did you? So when you defined the on-chip memory in QSYS,
yeah,
you gave it an offset of 0?
That's correct. Yeah, this is curious. When the other demo I'm going to show is using this shared memory to do really fast VGA writes, that GPU with fast display from SDRAM example. And there too, I am still trying to wrap my brain about how the memory mapping for this on-chip SRAM in particular is working, because that demo works, but Based on my understanding, I feel like it shouldn't. And clearly my understanding is wrong because it works, but I haven't figured out what precisely I'm missing yet. I was going to present that to see if you or any of the folks in this class perhaps know more about this particular thing. But in any case, yeah, we put this at an offset of 0, and then in the HPS code, we map it to this base address, FPGA on-chip base, which lives at C8. And then we read at that base address and then 1 above it to get address 1. And that all works just fine, but it's curious. In any case, I can keep going through this example, but I'm just letting you folks know that I'm wrapping my brain around this. And when I figure out what I'm missing, I'll report back. In any case, we do this memory address that looks very similar to those that we were doing for the PIO ports. And then down here, all that we do is we do a scanf to ask the user for an integer. We write that value to address 0 of that shared memory. And you'll recall that that's the signal to the FPGA to start doing stuff. So we write this to address 0. We wait until, so we write a non-zero value into address 0, and then we wait until we see a 0 value in address 0, which is the FPGA's signal back to the ARM that it is finished. And then we do a read from the values in address 0 and address 1. And the expectation is, say I type 5 in. That means we've placed 5 into address 0 of that shared memory. The FPGA sees that, increments it by 1, and puts 6 into address 1, and then zeros address 0 to tell the ARM that it's done. So when we print this out, the expectation if I type 5 will be the contents of address 0 is 0, and the contents of address 1 will be 6. It will be whatever I typed incremented by 1. So if we run this, if I type 1, we can see that at address 0, the contents are 0 because the FPGA has seen the 1, incremented it, put it in address 1, and then zeroed address 0. So by the time we read this out, this is back to 0. And the contents of address 2 is whatever we put in at the user terminal incremented by 1. Put in 5, we get 6. Put in 100, we get 101. Okay. And as I mentioned before, this is just addresses 0 and 1. You could have lots of addresses that you're sharing between the ARM and the FPGA, if you so desired. Are there any questions about this?
Can I see your the address file that you used to link the C to the?
This here?
So the SRAM base is C0. Okay, this has the on-chip end commented out there, on-chip span. So let me see the C again now. So where did the on-chip base come from?
On-chip base is defined here.
I don't know why that works, because I just went back and looked through an example I did, and as far as I can tell, it's got a match. So I don't think there's anything special about the C8, but I don't know why it works.
Is it your expectation that if it is the case that this is being placed essentially, if I'm understanding this, we should have been able to put SDRAM base here.
I believe so. Why don't you try it?
I'll try it.
That's easy to do, right?
Yeah, it is easy. So let's do this. SDRAM base. Oops. Let's see if this works. Yeah, let's do it like this. I'll call this SRAM.c. And then I will put SRAM dots. Oops. Be in this directory. Okay. So let's see. I'll put 5. Oh, that works. Okay, well, that's really nice to hear because that that makes a lot more sense in my head.
So now the question is, why does it work? And if I had to just completely guess, I would guess that the C8 is such a high bit that something is optimizing away those address lines. But
Okay. I think you froze, Bruce.
I don't know. I haven't seen this before. There's.
Oh, there you're back.
I'm back.
Yeah.
So, oh, it says my internet connection is suddenly unstable. Oh, great. So I don't know why it worked unless there's some, some bits just aren't being implemented at high memory.
Okay. So then let me just clarify. Let me correct what I had said incorrectly, and you can make sure that you agree with this as well. If we put this on-chip SRAM at an offset of 0 in QSYS, that is an offset from 0 from the AXI base address, which is the same C0 that it was for the PIO ports that we were experimenting with and everything else. This is not, just because this is on-chip SRAM, this is not being put at any different base address than anything else that we put on the AXI bus was. Okay. Okay, hopefully that's clear. Sorry, folks, for the little bit of confusion there. Do people have questions about this? The state machine on the Verilog side for controlling this stuff is pretty simple and very much like those that you've written for M10K block. So there's nothing really mysterious there. Okay.
If I can just insert a comment, I really like this method. If you have more than about 6 or 8 parameters you're passing back and forth, implementing it as parallel I/O ports gets tedious and bulky, whereas this is really compact to code.
Okay. So then I thought what I would do next is show an application of this, which is using this shared memory to make writing to the VGA screen much faster than it was in Lab 1. But in order to do that, I wanted to remind folks what we were doing in Lab 1 with the VGA. So let me just open up, I'm finished with this one. So I'll open up the QSys. So for Lab 1, your QSys setup will have looked much like what I'm about to show you. We had the VGA system pointing to SDRAM, and then we were using the HPS to write to that SDRAM, and the VGA subsystem was accessing that same memory that we were writing to from the HPS, and using that to put pixels on the screen. Which means that there was a, we were communicating all of the information that we wanted to write from the ARM to the FPGA, which meant that it was comparatively slow. So if we take a look at this, we had this, we had our VGA subsystem, and the pixel DMA master, the input here, or the master that is going to some slave memory address to get pixel information was tied to this SDRAM. And in the C code for this, you'll recall that when we were doing things like writing pixels, okay, we were writing to offsets from this VGA pixel pointer memory address, which was offsets from the VGA pixel virtual base, which lived at the SDRAM base, okay, which is that hex C00000. So we were using, we were storing the VGA pixel information in this SDRAM and then pointing the VGA subsystem to that SDRAM to go access it and draw things to the screen. I want to show you another example that uses the shared SRAM that we were just looking at. I'll keep that open. Sorry, there's a lot of Cordis windows and QSys windows flying around. We'll take a look at a different QSys arrangement that utilizes the shared on-chip SRAM. So this system that I'm opening up is going to have two of those on-chip RAM blocks dragged onto the bus here. So there is one here, this on-chip SRAM block, which looks exactly like the example that we just put together. One of the slaves is exported into Verilog. The other one is tied up to the AXI master. And then there is another one down here with one of its slaves exported into the Verilog and the other slave being accessed by the VGA subsystem. So in this case, the VGA subsystem is looking for pixel information in this on-chip memory. And in the Verilog, the way that this is working, this Verilog is set up essentially as a speed comparison between using the HPS to communicate pixel information over to the FPGA versus doing all of the VGA driving in the FPGA and leaving the HPS out of it. And what it shows is the speed increase that you get by doing all of the VGA pixel driving action solely in the FPGA as opposed to from HPS to the FPGA. What we'll see is that you can get speeds that are a little over 8 times faster by keeping everything in the FPGA. So we'll look at this state machine. What we're communicating from the HPS in this example is the corners for boxes. So in one of those on-chip memory blocks, we are passing in the X1, X2, Y1, and Y2 corners for a box. So the Verilog is accessing the first few addresses of that on-chip memory to get that corner information. But then once it has the corner information, I'm sorry, things I'm scrolling through quickly here. I'm scrolling through it quickly because it's like we just looked at, but I should make that explicit. We're looking at a particular address. We're deasserting the write enable, dropping into the next state, waiting for a state, and then getting the information out of that address and storing it in the data buffer. And these different addresses are being interpreted as different pieces of information. So again, address 0 is just being used as a handshake, but then address 1 is where the X1 corner of the box that we're going to draw is being communicated. Address 2 is where Y1 is being communicated. Address 3 is where X2 is being communicated, and address 4 is where Y2 is being communicated. And then the next one is the color that that box should be. So we're just reading through a few of those memory addresses like we just saw, getting out X1, X2, Y1, Y2 corners of a box and the color that that box should be. But then we're doing all of the actual writing to the VGA screen in Verilog. So what we are doing is we are setting the VGA X coordinate to X1, the VGA Y coordinate to Y1, and then dropping into a subsequent state, which sets the address of that other SRAM block, the one that the VGA subsystem is pointing to and is reading from. We're setting the address in that block to the coordinate that where we want to store the color information for that block, just like we were doing from the HPS for lab 1. Remember that the address corresponds to a particular pixel, and the information in that address corresponds to the color. We're doing exactly the same thing here. We're just storing it in on-chip SRAM as opposed to SDRAM, and we're doing all of those memory writes within Verilog. So we're setting the address by putting it at an offset from the VGA base address. And this offset is exactly like we saw exactly like we were doing in C before. The information that we write to that particular address is the pixel color. And we loop through every pixel contained in that box, writing that color until we're finished with all of the pixels. And then we go back up and we wait for another box to be communicated. Let me just run this quickly before we run out of time here. So I'll program this. And then if I run, what did I call the SRAM VGA? Let me open up a camera. So what this is going to do is the left side of the screen here is being written by the FPGA. The right side of the screen, it's just writing a bunch of random boxes. The left side of the screen is being written by the FPGA. The right side of the screen is being written by the HPS. and the time to draw these two identical images is being displayed at the top. And you can see that the FPGA was able to draw all of this in 42 microseconds, and it took the HPS 372 microseconds to draw the same image. And if we run this again, because it's randomized, we'll get different times, but the punchline will be the same. So let me run this again. So in this case, it took the FPGA 214 microseconds to draw this image, and it took the ARM, what is that? Almost 2,000 microseconds to draw the same image. And it's longer because the random rectangles that we happened to send over in this example were bigger rectangles. So there was more to draw in this case, which is why it took longer. But every time you run this, you will find a time increase of approximately the same fraction. You get approximately the same time, performance increase every time. Okay. So this is going to be particularly relevant for Lab 3 when you're drawing the Mandelbrot set, which we won't talk about the details of Lab 3 too much until maybe end of next week or so. I'm going to start introducing the Mandelbrot set, I think, on Monday. But this sort of, that Lab 3 is just all about speed. It's just how fast can you compute and draw. And a factor of, this is a pretty significant performance increase. So you will need to be doing your VGA manipulations in Verilog for Lab 3. Maybe using this on-chip SRAM like we just saw. The other option being that you could write a bus master to write memory to SD-RAM, for example. The on-chip SRAM is nice just because it doesn't need a bus master. You can just manipulate that slave directly. Okay. Any concluding thoughts from anyone? Okay. In that case, I'll see most of you in about 90 minutes, and I'll see the rest of you next week. Okay. Bye, everybody.